Albert Einstein, a giant of modern physics, had a complex relationship with quantum mechanics. He is celebrated for his groundbreaking work on the photoelectric effect, which helped give birth to this revolutionary theory. Yet, Einstein famously opposed some of quantum mechanics' most fundamental principles. He found the idea of a universe governed by chance and uncertainty deeply unsettling. He spent years grappling with its implications, leading to one of the most profound debates in the history of science. Einstein's skepticism centered on the strange phenomenon of entanglement. This concept, predicted by quantum mechanics, seemed to defy common sense and even Einstein's own theories of relativity. Entanglement suggested a connection between particles that transcended distance, an idea that Einstein found deeply troubling. His objections would spark decades of debate and inspire experiments that continue to this day. Imagine two particles, born from a single event. They are linked, no matter how far apart they travel. This is entanglement, a bizarre consequence of quantum mechanics. When we measure a property of one entangled particle, we instantly know the corresponding property of its partner, even if they are light years away. This connection is not some invisible force or signal traveling between them. It is deeper than that. These particles behave as a single entity, unified by an invisible thread woven into the fabric of reality. Their fates are intertwined, their destinies inseparable. Einstein famously called entanglement spooky action at a distance. He found it unsettling because it seemed to contradict his theory of special relativity, which states that nothing can travel faster than light. How could information travel instantaneously between entangled particles, even across vast cosmic distances? Einstein believed that there must be some hidden variables, some unknown factors that explain this apparent connection. He argued that quantum mechanics was incomplete, that a deeper theory would reveal a deterministic universe where events were not governed by chance. In 1935, Einstein and his colleagues Boris Podolsky and Nathan Rosen published a paper outlining their objections to entanglement. This paper, known as the EPR paradox, argued that quantum mechanics' description of entangled particles was inconsistent with the principles of locality and realism. Locality states that an object can only be influenced by its immediate surroundings. Realism suggests that physical properties exist independently of observation. The EPR paradox argued that entanglement violated both these principles. It suggested that measuring one entangled particle could instantly affect the state of its partner, regardless of distance, challenging the very foundations of our understanding of space and time. Section 5. Bell's theorem, a ray of light. For decades, the debate over entanglement remained a philosophical quagmire. There was no way to experimentally test whether Einstein or quantum mechanics was correct. Then, in 1964, physicist John Bell proposed a groundbreaking theorem that changed everything. Bell's theorem offered a way to experimentally distinguish between the predictions of quantum mechanics and those of a local realistic theory, like the one Einstein envisioned. Bell showed that if hidden variables existed, as Einstein believed, then the correlations between measurements on entangled particles would be bound by certain limits. However, if quantum mechanics was correct, these limits could be violated. Section 6. Testing the theorem, the first experiments. Bell's theorem paved the way for a new era of experimental physics. In the 1970s, John Clauser and Stuart Friedman conducted the first experiment to test Bell's inequalities. Their results, though not definitive, hinted at the validity of quantum entanglement and challenged Einstein's view. These early experiments were plagued by technological limitations, leaving open the possibility of loopholes that could still support hidden variables. However, they inspired a new generation of physicists to refine these experiments and close these loopholes. Section 7. Zeilinger's experiment, closing the loopholes. In the 1990s, Anton Zeilinger and his team at the University of Vienna conducted a series of groundbreaking experiments that dramatically improved upon earlier tests of Bell's theorem. Their experiments used pairs of entangled photons, generated from a special crystal, and sent to two separate detectors kilometers apart. To ensure that the measurement settings for one photon did not influence the other, Zeilinger's team used a random number generator to rapidly switch the settings while the photons were in flight. This ingenious setup closed a significant loophole known as the locality loophole, which had plagued earlier experiments. The results were astonishing. Zeilinger's team observed violations of Bell's inequalities that were far greater than those seen in previous experiments, providing compelling evidence for the validity of quantum entanglement and challenging the very foundations of our classical understanding of the universe. Section 8. The implications, quantum computing and communication. The implications of entanglement are far-reaching, extending beyond the realm of theoretical physics and into the world of cutting-edge technology. Entanglement is not just a bizarre quirk of the quantum world, it is a resource, a powerful tool with the potential to revolutionize fields like computing and communication. Quantum computers, which harness the strangeness of entanglement and other quantum phenomena, hold the promise of solving problems that are intractable for even the most powerful classical computers. Imagine designing new drugs, developing revolutionary materials, or breaking the encryption that protects our online data, all tasks that could be within reach with quantum computers. Entanglement also paves the way for new forms of secure communication. Quantum cryptography allows for the creation of unbreakable codes, ensuring that messages can be transmitted with absolute secrecy. This technology could revolutionize fields like banking, government, and military communications, ushering in a new era of unhackable information exchange. Section 9. Entanglement, a glimpse into the heart of reality. Einstein's quantum riddle, once a source of deep philosophical debate, is now leading to technological revolutions. Entanglement, once dismissed as spooky action at a distance, is now recognized as a fundamental feature of the quantum world and a powerful tool for exploring the universe's mysteries. As we delve deeper into the quantum realm, we are challenged to confront our classical intuitions and embrace a new understanding of reality. Entanglement suggests a deeper interconnectedness in the universe, a web of relationships that transcends our everyday experience of space and time. It is a testament to the power of human curiosity and our relentless pursuit of knowledge. A journey that leads us to question the very fabric of reality and glimpse the universe's profound beauty and mystery.